Welcome to the first lecture of this GIAN course, Elements on Smart Structures. I would like to start this lecture series with some current research on smart structures, and also like to introduce briefly TU Braunschweig, our institute, and the working group before, and we close with some organizational details about the course. And yeah, thank you again for coming, Al, and traveling through India to participate in this course. So, brief introduction of our university, of the TU Braunschweig. TU Braunschweig is a technical university which was founded in 1745. It's the oldest technical university in Germany, and it also belongs to TU 9, which is a cluster of the 9 largest technical universities. We have around 15,000 students and 2,300 researchers. Of them are 244 professors. So to give you a rough idea about TU Braunschweig. Where is Braunschweig located in Germany? I don't know, does anybody have been to Germany before? So, yeah, you have been, so one person. Where have you been? Okay, in Bavaria. So here in the south of the country. So Braunschweig is located really in the center of Germany. Here's our capital city, Berlin. It's in the east, maybe 250 kilometers away from Braunschweig. Here in green, this is the state Lower Saxony, where Braunschweig belongs to. And I grew up here at the border to the Netherlands. We have also quite some international students. Around 3,300 students are international from the 15,000 students overall. Also have additional campus in Wolfsburg, which is the city where the car manufacturer VW has his headquarters. And we have a campus in Singapore. The research at TU Braunschweig, which is more or less industry driven, as mentioned in the inauguration, is divided into 4 core research areas: mobility, metrology, engineering for health, and future city. And all these core research areas are interdisciplinary. So we have 6 faculties, and all of these faculties contribute to the 4 core research areas. As we are a technical university, we have an engineering focus. So we have the Carl Friedrich Gauss faculty for mathematics, also faculty of life science, faculty of architecture, civil engineering, and environmental sciences. Then the faculty where we belong to, our institute, faculty of mechanical engineering, and we also have electrical engineering and humanities and education. So as mentioned, we belong to the faculty of mechanical engineering, where we have 4 departments, and our institute, Mechanics and Adaptronics, is in the department Production and System Design Engineering. And we have 3 professors heading the institute. Professor Markus Böhl, who's more into biomechanics. Professor Christian Hühne, who's also working at German Aerospace Center and is more in aerospace structures, functional structures. And then myself, I recently joined the institute. So short introduction about myself. I have a bachelor and master's degree in aerospace engineering. During studies, I did some internships and student research projects at VW, Volkswagen, the car manufacturer, which is close by. And then 2017, after finishing the master's degree, I joined the German Aerospace Center, DLR, the Institute of Lightweight Systems, and did also my PhD there. And my PhD topic was simulation-driven design of bonded joints in fiber composite structures, in fiber composite aircraft structures using progressive damage analysis. And now, since a bit more than 2.5 years, I joined TU Braunschweig as an assistant tenure-track professor. It's a tenure-track to an associate professor, and the professorship is called Function Integration. And I still have a part-time contract at DLR, so I'm still connected to German Aerospace Center. And as Professor Chauhan also mentioned in the inauguration, a sustainable society is an important goal, and this is also the main research question I have for my working group. How can structural systems in future mobility become truly sustainable? And I think one answer could be by making them circular, smart, and safe, and this could be enabled by function integration. So now Henrik Traub would also like to introduce himself.
Thank you. So yes, my name is Henrik Traub, and I did my bachelor's and master's degree between 2010 and 2019 in aerospace engineering. Also at the Technical University of Braunschweig, where I finished with my master's degree at the German Aerospace Center for the optimization of composite structures. Then, in between, I did my internship student research projects also at Airbus, developing also wing optimization, but aeroelastic wing optimization, which then also led to my master's in structural optimization to connect the aeroelastic and the structural optimization parts. And since 2019 until this year, I was a research associate at the Institute of Mechanics and Electronics, and I did my PhD. Called Triply Periodic Minimal Surfaces for Surface Structures for Laminar Flow Control, with my supervisor, Professor Christian Hühne, who is also a supervisor at the Institute of Mechanics and Electronics. And since this year, I joined the team of Professor Völkering, doing renewable structures. Okay, and as I mentioned in the inauguration, I will care about the lab, and we brought a lot of lab equipment to here. It's already set up downstairs, and later on I will give you a small safety briefing for the lab, because we work with high voltages, and there are some rules you need to check, and but let me come to that later on. Thank you.
Thank you, Hendrik. So we go ahead presenting the group. The research work in the group can be clustered in 3 major clusters to get to smart, safe, and virtually tested circular structures. So we have the first cluster, which are smart and safe structural systems. Trying to answer the question, how can structures detect, understand, and prevent damage to extend their safe lifetime? Then we have the bio-based and recycled materials for circular structures. So how can sustainable materials become reliable enough for structural applications? And then the third pillar of third cluster is digitally assisted material characterization and virtual testing, with the question, how can we qualify circular materials and interfaces faster with fewer tests and less weight? And to give you an impression, I would first introduce the group with some faces, the persons who are doing the research, and then show some example projects. So the group with the 3 pillars consists of 9 people. Julian Steinmetz and Henrik Traub are postdocs, and the other 6 persons are PhD students I supervise in the group at IMA. So first cluster, smart and safe structural systems. This is closely connected to my own PhD topic. I worked on bonded joints for aircraft structures, for example, longitudinal fuselage joints, which are not possible or not ready for certification yet, primary bonded joints. We have to have some rivets at the moment to at least carry limit load. And one idea to solve these problems is to have a smart structure, a multifunctional joint. And in this fiber composite structure, we have the adhesive bond line here in the middle. And we have these blue elements. And the blue elements are the multifunctional elements which are made from a thermoplastic material. And also sensing structures are integrated. And the idea is that these elements made from PVDF can stop cracks growing in the adhesive bond line. So they replace the chicken rivets, and they can also sense a crack when it grows towards the middle of the bond line or towards the multifunctional element. One more slide on the multifunctional adhesive layer. So we have here a side view or cross section again from the bonded structure. Here is the bond line in the middle. We have two rows of these multifunctional elements made from PVDF and the CFRP structure. And you can see here from above the sensor structure made by the Institute of Microtechnology from our university. And then we performed these kind of tests, which is a crack-lapped shear test. So it's you apply a tension load on both ends, and then a crack grows in the bond line. And the idea for sensing is now that we have these two rows, and if the crack reaches the first row of multifunctional elements, the strain signal rises, and this one keeps at a low level. So the difference between these rows will tell us that a crack is growing inside the structure. And we also virtually tested it with finite element simulations and had a quite good agreement between the sensor signals from the experimental test and also from the simulation. Then the next topic in this cluster we are working on is moisture monitoring in hemp fiber reinforced polymers with embedded capacitive sensors. Natural fiber composites are prone to moisture uptake, which impacts the mechanical performance. And the idea is to integrate commercial, or in our preliminary study, we integrated commercial capacitive sensors for moisture monitoring, and then performed 4-point bending tests and also some double cantilever beam tests, so mode 1 crack growth. And try to correlate the moisture content to the bending performance. So we saw that moisture uptake will decrease the flexural modulus in this case. And we also investigated if the capacitive sensor impacts the structural performance. So is it a weak point in the structure or not? And we saw some impacts on the mode 1 crack growth, and the next step is in a project to develop an own sensor with a paper-based substrate, which is thinner and does not impact the structure that much. This was already a smart structure with natural fiber composites, and the next cluster is all on bio-based materials and recycled materials. And there we had a study and tried to investigate if upcycling post-consumer jute coffee sacks can be used as composite reinforcement. So is it possible to use post-consumer coffee sacks to have a reinforcement effect in the laminate? And we did this by comparing the jute composites to flux unidirectional specimens and flux cross-ply specimen, and also to, at least in Germany, typical birch and beech wood, again under 4-point bending. And we saw that the flux unidirectional material is performing quite well in bending, and it's comparable to wood. The cross-ply, which is so 0 and 90 degree plies, which is a fair comparison to the Hessian material from the jute coffee sacks showed that the primary natural fibers are performing much better than the jute, but we had at least some reinforcing effect compared to the neat resin. So maybe for low load applications, it is possible to use these jute coffee sacks from waste to create new composite materials. And the challenge is, you can see here the primary flux material, which is quite even and homogeneous, and in the coffee sacks you have some defects and imprint, and also untwisted yarns, which impedes the mechanical performance. And same goes for the flexural strength, which is also higher than the neat resin, but not so high than the primary natural fiber materials. Another topic in this cluster are wood NFRP hybrids. We had the question if flux PP tapes could be used to increase the bending strength of wood, to upcycle used wood and realize the original mechanical performance again, and had some preliminary tests and used thermoplastic polypropylene tapes, flux reinforced, and got a good, let's say, adhesion between the wood and the NFRP, and the study is ongoing to see if we have a real reinforcement effect. Then, here's a animation missing. A question the car manufacturers in Germany at the moment have, because of EU regulations upcoming, are the use of recyclate materials, also post-consumer plastic recyclates. And the question is how to, let's say, calibrate the mechanical performance of the material. The recyclates have different mechanical performances from batch to batch, and you can mix it with virgin material where you know the mechanical properties quite well. And we did a preliminary study on a car roof handle and tried to optimize the cost, performance, and CO2 footprint by mixing virgin material with recyclate material and try to find the, let's say, right share between virgin and recyclate material. And with our assumptions, we found out that, let's say, the cheapest part has the highest carbon footprint in the take and make phase, and the part with the lowest footprint in the take and make phase has the highest footprint in the use phase. So, but the assumption were based on some literature data. So this is also an ongoing study, but we try to give industry tools to, let's say, enable the use of recyclate materials for the upcoming European regulations. So then we have the last cluster, digitally assisted material characterization and virtual testing. Again, the polymer recyclates, we are looking for rapid characterization. If you have batch-to-batch differences in the mechanical properties of the material, you have to have fast ways to characterize the material and not spending much money on an overall characterization campaign with many tests. And the approach we follow is called in literature material testing 2.0. So the idea is that you have a more complex specimen than a uniaxial one and combine it with digital image correlation. So you capture during testing the whole strain field and not just points by strain gauges. Sorry. And then use inverse identification methods to to get more than one property out of the test. And we started with a t-test, a test called t-test, which is has here boundary conditions left and right, and here you apply a tension load, and then in this T-shaped test specimen you get different regions. Here is a tension region, here above compression region, we have a shear region, and also biaxial tension. So you can get tension and compression properties at first-hand stiffnesses, so modulus, Young's modulus, and you can get shear values. And with the material under investigation, again, PP, we performed some simulations, finite element simulations of these tests, and we also saw the different regions for compression, for tension, and for shear, like assumed when designing the specimen. And then the next topic in the virtual testing cluster is also based on my work back at DLR, so the bonded joints. There we try to get a tool chain for bonded joints. Here this is a single lap joint, so simply overlap bonded joint. And we have 3 simulation modules, perform an impact simulation to get an initial damage in the structure, for example in aircraft structures a tool drop, then map these damage to a fatigue simulation under cyclic loading so that this initial damage will grow, and after the desired cycles under fatigue we again map the damage to a high fidelity residual strength simulation where we then assess the residual strength with the damage from impact and fatigue, so that we have a virtual impact fatigue residual strength tool chain. And with that, I have some slides more here on this topic. We are responsible for the residual strength simulation, and we performed some validation experiments. Here's a UTM, universal testing machine, with again a single overlap joint, but a bit wider than a standard coupon, so 100 millimeter in width here. And we inserted a release film to have an artificial damage in the structure, and then performed the test and saw a very complex damage pattern through all the layers, or up to the first 0 degree layer. And this test was also simulated with our simulation tool chain and the residual strength simulation. And it not only predicted the strength and stiffness of the specimen quite well, but also the damage pattern. For example, here is a 45 degree ply where we see this damage inclined by 45 degree, and this corresponds well to these areas which are also 45 degree plies. So we could also predict the damage pattern after the test. So, and with this, we are back at the image from the beginning. The multifunctional bond line, this is the next step to also include these multifunctional elements in the virtual testing environment. And we are at the moment characterizing this PVDF material so that we can capture also the effect of crack stopping in this simulation tool chain, and are then hopefully able to virtually test also these smart structure with this multifunctional elements. So this as a brief introduction to our institute and also to the working group. And now we go ahead with the details on the GIAN course we have this week. So first we will have a look on the schedule. I think you all got it in your kits. So we are at the moment here, current research on smart structures. We will have additional 3 lectures today, elements of smart structures, multifunctional materials, and operating principle of piezoelectric transducers. And then in day 2, Tuesday, we start with the labs. We have then the theoretical background to perform the labs. So we have one lab after the tea break and one lab in the afternoon. And then on day 3 and 4, we also have the labs 3 and 4 with the experiments Henrik will take care of. Then we close with further applications and summary and wrap up, and we will have the exam on Friday morning, afterwards the evaluation and grades and concluding remarks. Then unfortunately we have to leave to be back to Germany, and on December 20, so on Saturday, there are 2 more lectures held by Professor Chauhan and Professor Kumar from IIT. And then the course overall closes with a certificate distribution.
Evaluation will be required to be held?
Sorry?
During the evaluation?
Yeah.
So who will do the evaluation?
We will do the evaluation. So Hendrik and I will. Sorry, I.
Evaluation?
Yeah.
Are we required to be there during that evaluation?
No, I understand. So no, the exam is here in the morning. I think we have to extend it to from 10 to 11 because the exam will be 1 hour. I have a slide on the exam, and then during evaluation, Henrik and I will have the time to check your exams and grade it. So you have free time here, and then you come back for this grades and concluding remarks slot.
Exam will be multiple choice?
I will. We skip the safety briefing and go to the exam slide. So what to expect in the exam? So the format is a written exam, so no multiple choice. You will have to give 3 answers, let's say, to the questions. You will have 60 minutes for the written exam, and the question focuses on the learning objective and the key concepts. And before each lecture, I will have a slide with the learning objectives, and then again a summary which corresponds hopefully to the learning objectives. And we emphasize on understanding, not memorization. And yeah, the minimum requirement is 50% of total points. And Henrik and I will then check the exam in this evaluation block, and then you get the grades. Is the question answered? Or okay, perfect. So then we jump back to the safety briefing for the labs, and this will be done by Hendrik, since he will take care of the lab.
Concluding remarks you can produce
So it is concluding remarks before lunch. Yeah, we will check if this is possible.
Wie gehe ich von zurück?
Zurück.
Okay. Okay. Regarding the safety briefing for the labs, maybe up front, as I said in the morning, the most important thing is the high voltage. So I ask every one of you to be aware of high voltage, because I don't want to disconnect any one of you from the high voltage. Okay, so yes, safety briefing for the labs. So before we start in the lab with everything, mainly I do that, but I want all of you, as I said, to be aware of it. Contacts of high voltage cables must be checked before you use anything. If we get a short circuit in that could be dangerous for you or for whoever touches that. So we need to check that the contacts are fine and all cables are connected as they should be. the high voltage amplifiers we installed, they range up to 2 kilovolts, and they should only be turned on in front of the experiment, and then it shouldn't be forgotten that they have to be turned off after the experiment. So just in case anyone wants to show something and then you touch it and then it's still high voltage, it's turned off. So this is very important. We usually use BNC cables. I guess you know more or less what BNC cables are. We usually use BNC cables in the experiments, but we have special high voltage cables, and they should not be touched. And also all piezoelectric sensors and actuators should not be touched, since they have open metal parts. If you touch them, you connect to the high voltage. So please, in experiments, before, after, if you ask, no problem. We can also take at hand some piezoelectric actuators and material sensors, but in the experiments, please don't touch them. And before you turn something on, you may ask me or Professor Völkering if you can turn on a machine so that we can double check all values. Okay. Yes, and then not that important, 0.7, because we do not really have that. So there have to be some distances between sensors, rotor, and catch bearing, but we do not use rotors in the labs this time. So this is basically invalid. So please try that if we do the experiments, they're all set up on tables, that you don't put things on the table that is not part of the experiment, so we don't lose the overview and we actually see what is there and what isn't. And we can't allow eating and drinking within the lab close to the experiment. So please do that in front or after the labs. Yes, and then obviously instructions of the lab supervisors must be followed, and if not, repeated violations may result in exclusion. I don't think we will come to that point. So everybody of you should have in his map a page to sign. And for the first lab, I ask you to bring the signed page to the lab. We will collect them and keep them, that you all read these rules written here, and that you sign that you have written the rules and that you understood the rules. Okay? So this is a formality, but it's for us and for insurance purposes, I think it's important to have it. Thank you.
So do you have any questions regarding the safety briefing?
Oh, yeah.
Okay.
Good.
So since we are a bit ahead of time, we may use also, after finishing the time before lunch, that you can read through the safety checklist and sign it, and then we collect it after this session. Then we already have it done. Okay. Then exam slide again. I think we already spoke about it. Do you have any more questions regarding the exam? Not yet. Okay. We may prepare also some example questions so that you get an impression what a question could look like, so that you can prepare. Okay, then thank you very much for the first lecture, for the introduction. I hope you get an impression about TU Braunschweig, our institute, the working group, and what the course would look like. And in the block after lunch, we will then start with the smart structures itself. So thank you very much. Yeah. Yeah. So that's a good hint. So if you have read through the safety checklist and have signed it, we could take the minutes we have to go over to the lab. Then you know the room already, see the setups, and then we have the lunch break. Okay, thank you.